What's up, you pussy-ass pussies? My name is Flynn Wilson. This is a motherfucking Flynn Wilson podcast. What are you bugging it? Yeah, look at my ducky. Look at my little ducky. Look at her. Bless you on the table. Yeah. She thought that I was talking about someone. She thought I thought someone was here. Her name is Jazz. She's very cute. There you go, doggy. Let's do some schoolwork, pussy. Doing some different stuff. Doing some fame and technique stuff. So I've listed down. I went through 2013, 2014 exams for everything. Good practice. Listed down all the stuff that I'm bad at. Now I'm gonna have a few days where I just do that stuff. Today is the 10th of November, 2021. It's a Wednesday. So let's go over everything. Let's go. Shape of molecules. Molecules, square, planar, C-saw and all that shit.
Let's say that to use this video.
Dude, why is he? His body's looking fucking weird. What?
You're gonna need this table. If you don't have
Has
that,
he been like green screen out? What the fuck is going on with his body? Random bicep video. Gonna watch that. Vaporization, combustion. Formation, enthalpy changes. That one's an hour long, probably won't watch that. This one. This video. Heaps of videos. So real quick, watch this do tear of bicep. Oh my god. That was that worst case scenario. Yeah, fucking fell over on his fat ass.
standard.
Heaps of good videos and I'm finding entropy and entropy. Okay. Let's watch all these videos, huh? Oh yeah, let's go.
He knows a lot about the science stuff, Professor.
Shut the fuck up, Professor Dave. Let's combine all these things. That will be the title. Yep. Deal. Okay. Firming technique. All the stuff I gotta do. Cool. Alright.
Enthalpy change of formation.
What about the Anki flashcards as well? They're gonna be pretty important. So make some flashcards. Let's learn some stuff. Feynman technique, this bitch. You know what I'm saying? Add. It's demo chemistry. There you go. And here we go. Ready to study, pussy.
Delta HF. So the definition is, the standard enthalpy change of formation is the enthalpy change that occurs when 1 mole of a substance is formed from its elements in their standard states under standard conditions.
Occurs when 1 mole of a substance is formed from its elements in their standard states and conditions. Dope.
And standard conditions are 298 K and 101.3 kilopascals of pressure. So we can use standard enthalpy change of formation values to calculate the overall enthalpy change for a reaction. And we can use this equation. So it's the enthalpy change is equal to the sum of the standard enthalpy change of formation of the products
Hopefully they just give me an equation. Come on. Come on. Give me an equation.
minus the sum of the
Just give it to me. Sum of symbol. Oh my god, it's sigma. Delta symbol. All I want is a triangle. Just give it to me. Ooh, 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 say ooh. Where's delta? Delta. Give it to me. Ooh, ooh, ooh. Ooh. Oh my god, triangle symbol. How are you guys fucking up shit so bad. Oh my god, please don't be. Jesus Christ. How do I take Google Chrome out of black mode? Be white. Stop being black. I hate black. Paste anywhere. Oh my god, this is 8. This is fucking 8, cunt. Deltas. We'll say how to take Google Chrome out of dark mode. Thank you. Oh my god, what the fuck? This is a terrible study. Dude, why the fuck is it black? Has it always been black? Make it fucking white. Fuck black. Whatever. Okay, click on fucking settings. Okay, dope. Go settings. Why is it so laggy now? And it just says turn off dark mode. What the fuck? What the fuck is dark mode now? I can't fucking see a picture of dark mode. It's dark mode, man. Oh my god. I just fucking hate it because when I fucking copy and paste shit, When I copy and paste shit, it doesn't fucking copy and paste right. It's like fucking black. Black and white. This is fucking AIDS. The whole text is now black and white. This is fucking terrible, man. It doesn't let me copy this. Copy, paste. Okay, there you go. That's my AIDS. Dope. Fucking finally. What the fuck is that? Ooh, 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 ooh. Don't worry about it. That was just the courier guy. Picking up my package, baby. Oh my god. I made this way more complicated than it should have been. Ew, 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 ooh. Don't worry about it. Okay,
Standard enthalpy change of formation of the reactants. We can find the standard enthalpy change of formation values in the data booklet. And the last point, the free elements, such as oxygen or hydrogen, they have a value of 0 because they are not forming from anything, because they are just elements. So let's try an example. We're going to use delta HF, so standard enthalpy of formation values, to calculate the overall enthalpy change for this reaction. So we have C3H8, which is propane, and it's burning in oxygen gas to give carbon dioxide and water. And I've written in the standard enthalpy change of formation values from the data booklet. So for propane, it's negative 105 kilojoules per mole. Oxygen is 0 because oxygen is an element. Carbon dioxide is negative 394 kilojoules per mole, and water is negative 286 kilojoules per mole. But because we have 3 moles of carbon dioxide, we multiply the value in the brackets by 3. And the same for the water. We have 4 moles of water, so we multiply everything in these brackets by 4. So here's the equation that we use. The change in enthalpy equals the sum of the standard enthalpy change of formation of the products minus the sum of the enthalpy of formation of the reactants. So when you add them all together, you get negative 2,326 minus negative 105, because the 105 is the propane, is the reactants, and the total we get is negative 2,221 kilojoules per mole. So that's the change in enthalpy of this reaction using standard enthalpy of formation values. Next is the standard enthalpy change of combustion, which is delta H comb. Comb means combustion. So the definition, the standard enthalpy change of combustion is the enthalpy change when 1 mole of substance burns completely in oxygen under standard conditions.
Conditions. Oxygen. Dope. Oh, what? Make it a basic card. Red.
And here's the equation that we can use. So it's the
Right, so it's the exact. Oh, fuck's sakes. Okay. Oh my god, no. No, sum of symbol. Oh, not this again. Sigma. Don't you worry about it. Cool. Ooh, that's some weird shit. Make it a close. Bang. Bang.
The change in enthalpy equals the sum of the standard enthalpy change of combustion of the reactants minus the sum of the standard enthalpy change of combustion of the products. Now, you may recall that the previous example where we used delta H of formation values, it was products minus reactants.
Oh, fuck. Okay.
When you use combustion values, delta H combustion values,
Oh.
it's reactants minus products. So here's an example. We're going to calculate the enthalpy change for this reaction, and we're going to use standard enthalpy changes of combustion. So this is ethene reacting with hydrogen to make ethane. And I've written in the values all in kilojoules per mole. So it's negative
What the fuck is this fucking combustion?
111, hydrogen is negative 286, and ethane is 1560. So here's the equation that we use, and we're going to add up the sum of the standard enthalpy changes of combustion for the reactants. So the reactants are obviously on the left side of the arrow, minus the sum of the standard enthalpy changes of combustion for the products on the right side of the arrow. So when we substitute in the values, we end up with negative 1697 minus, and in brackets, negative 1560. And that gives us an enthalpy change using standard enthalpy changes of combustion of negative 137 kilojoules per mole.
All right. Don't you worry about it.
Energy, the foundation of the universe. We'd literally
fuck up,
be
you fucking
nothing without
pussy
it.
fuck.
It does all our work, provides all our heat, can be stored to use later, and never ever goes away. Sounds like the bestest best friend ever.
Oh, oh, oh. Ah, ah, ah. Eh. Ooh.
Sir Dave explains.
It's Professor fucking
Okay, what-
Dave. Alright. Let's take a break. Ew, ew, ew. Ah, ah, ah. Eh, eh, eh. Ew. Don't you worry about it. Ooh, 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 ooh. Ah, ah. Katie, you've got your pajamas on. Hey, what's this? Oh, look, it's my new toy. I got a toy for something. It's a toy. This delivery guy. No, I was delivering something. So I gave him a parcel. What's this? Where's Jazz? Is she outside? She hates this toy. What are you doing? What are you doing walking out there though? It's just like pointing out ads there. Because he said he's going to teach me to point out ads. Is it right though? Is it right though? What I see? Or it's just like pointing out ads? Are you going to have to do it? I haven't done a parallel park. That's hard because there's seven. This is like opposite how it should be. Why the fuck am I paying for it? Yeah. I'm not actually paying. I'm not paying for it.
Your rent is a lot more affordable.
I'm not actually paying rent. Like paying for that don't work.
Ooh, ooh, ooh,
Dad.
It's working.
Oh yeah.
Where's
I
Jazz?
forgot he has a job.
Where are you eating that?
In my room.
Why?
Jazz is in the lounge. I thought he was taking Jazz for a walk. Was I gonna find him? Oh wait, Jazz is still outside.
Just leave her outside, or the door's open. Just leave the door open. Alright. Let's do some practice questions, pussy. Oh, Katie. Hey, come in here. Come in here, Katie.
What?
I've got this,
I don't want to be in your stupid video.
I've got this, like, I'm doing these, like, podcasts, kind of, where, like, I just go on photo booth for, like, an hour and just kind of, like, talk while I study. So come here.
You're doing a podcast. Are you
Yeah.
actually joking?
Come here. So in the future,
Oh, thank God, I look really good right now.
we'll be able to look at this and
Is
see what it was like.
Is this actually recording?
Yeah, don't stop
No,
it.
it's not.
Yeah, there's like
You
you can
haven't pressed
see
record yet.
32 minutes.
Oh.
My sister's a bit silly. So in the future, I'll be able to look at this and see how much I've changed.
Okay.
All right, it's good to see my sister, huh? Well, tell them what you're doing.
Just vibing.
Tell them what you're doing right now. Tell them what you just told me.
Who's them?
I don't know. Anyone who's interested. Probably just me.
I
Tell my future self what you're doing right now. You
Um,
working? You at school?
I'm working, but I just finished my degree.
She just finished her degree. Don't cough on me, you fucking.
I'll give you Corona.
Her degree in what? What did you even? I don't even know what you did.
You don't even know what I did.
Nah, like a
You're such
criminal
good brother.
psychology or something.
You're such a good brother. You don't even know what my degree was in.
Wasn't it criminal psychology?
It was criminology and education.
Criminology and education. So what are you gonna do for a job?
Something
What is your dream?
intelligence.
What is your dream job with your degree?
Actually, dream job is just capitalist propaganda. There's
What
no
does
such
that
thing as
mean?
a dream job for everyone.
What does that mean?
Like, because heaps of people are very complex and they have lots of different skills, and it's a bit silly to
Oh my
say
God.
that there's one job that's suited to them.
Oh my god, true.
So deep.
Alright,
I'm
well-
gonna fuck off now.
Okay, bye. You can close the door if you want, but I'm gonna be talking myself anyways. Or is Jazz inside? Did you leave the door open?
Let's do some
Ew. My sister. Cuckoo. She's crazy. She is crazy. Who is going to employ my sister? Don't worry about it. Ooh,
practice
ooh,
regarding
ooh.
enthalpy of combustion. So the question asks, how much heat is released upon the combustion of 1.00 liters of isooctane?
Oh, yeah?
And that has the formula C8H18.
No way that's the only fucking information we get. We gotta get like we'll get the combustion, the enthalpy of combustion for like...
Now, in order to answer this question, we will need to know that the density of isooctane is
What the fuck?
0.692
Density?
grams per milliliter.
Nah.
And we also need to know that the delta H of combustion for isooctane is negative 5,461 kilojoules per mole. So if this is all the data you need, go ahead and give this a try. So
I don't
let's
think
start
this
out
isn't
with
what I'm. This isn't what I'm doing. It's density. I don't use density. Fuck density. The only thing dense should be me, because I'm fucking massive. This video
Hello,
is
and welcome back to another video.
Stop. Okay, this is all getting well confusing. I've got too many things open. I'm going to close this. I'm going to close my photo booth. I'm going to drag this into the same tab. Then we're vibing. We're chilling.
Ever. And yet, most of the time, we take it for granted. But here at Crash Course, we feel bad for our old friend Energy. We want to understand it
This guy's
so
a
that
fucking pussy nerd, but...
we can be a better friend to it. And also so that we can understand what it's trying to tell us. Like that any bond between two atoms contains energy. How much energy? Well, that is not the simplest question to answer. And yet, today we shall answer it. Kinda. Using a nifty little thing called enthalpy. Last time, we learned about internal energy and the two ways that it can be transferred, by heat or by work. And heat and work are useful concepts, but they have limitations, particularly that it is extremely difficult to figure out how much of which one is being done. Work is energy transferred to the motion of objects, while heat is energy transferred to the motion of atoms and molecules. But figure out how much of which one is being done. Work is energy transferred to the motion of objects, while heat is energy transferred to the motion of atoms and molecules. But for any given change in energy, the split between work and heat could be pretty much anything, as long as there's some going to each. Say my car is at the top of a hill and there's a frozen banana stand at the bottom. If I roll down with my brakes on, lots of heat will be transferred into my brake pads and my brake discs, and I will kind of like very slightly knock into the frozen banana stand, doing a tiny amount of work on it. But if I am reckless and insane, very little heat will be generated and my car will do a huge amount of work on the frozen banana stand. Both paths transfer the same amount of energy, but one produces very little heat and the other produces a ton. And so we say that heat and work are pathway dependent. The amount of heat or work done depends on the pathway you take. The change in energy, on the other hand, is the same in either case. Change in energy is independent of the pathway. In chemistry and physics and math, we call that a state function, because the only thing that matters is the starting state and the ending state, not the stuff in between, not how you got there. State functions are pretty great because they make the math very simple. It's just one amount minus another amount. It would be pretty fascinating to know exactly how much energy is tied up in a molecule. Unfortunately, it's next to impossible to know that number. It's too big, and there are too many boxes where all that energy could be hiding. It's like trying to measure the total volume of the ocean. Like, good luck. However, since energy, like volume, is a state function, we can very easily talk about the change in energy. Just like if you dump a 2-liter Mountain Dew into the ocean, you can't tell me how many liters are in the ocean, but you can say that that number has changed. It has just increased by 2. In the same way, we're interested in energy being transferred in or out of a system because of chemical reactions. And in many cases, all we're interested in is the heat part. For example, if I burn a pile of wood, I care about the heat being generated, not the work being done by the volume increase or by the rising smoke. So dealing with the whole internal energy equation would kind of be overkill. What we really need is a state function based on the loss or gain of heat in chemical reactions. Which, yes, is what enthalpy is for. In addition to being a silly-sounding word, enthalpy, which is represented by an equally silly capital H, is technically the internal
Fuck are you talking about?
energy of a system plus the energy that's required to sort of shove the surroundings out of the way and make room for the system's pressure and volume. With enthalpy, we can make some assumptions and do some fancy math to make the simplest equation we've ever seen in Crash Course Chemistry. Let's get there real fast. So first, we're not really interested in the total enthalpy of a system, which is good because it's impossible to measure. We're really just interested in how much it's going to change as a state function. So the formula for enthalpy is usually written as change in enthalpy. Delta E, or change in energy, equals Q plus W, so we can replace that part, and then we can make two big, huge assumptions. First, that pressure is constant. Fortunately, despite talk of high and low pressure weather systems, atmospheric pressure really changes very little compared to the other terms in the equation. Constant pressure is a pretty good assumption here on the Earth's surface, so that last delta only applies to the volume. The second assumption is that the only work done in the system is the work that the pressure does to change the volume, known as pressure volume work. So W equals negative P delta V. Now the signs are a little bit weird here. An increase or positive change in volume results in an output of work by the system, a loss in internal energy, which is defined as a negative amount. So the signs for work and for P delta V will always be opposite. And so voila, the P delta V parts cancel. Delta H equals the heat of reaction. Change in enthalpy is equal to the heat gained or lost by the system. So I guess in the end, the capital H for enthalpy does kind of make sense. Thanks to this little trick, for a lot of reactions that happen at constant pressure, like here on the surface of the Earth, working just with enthalpies instead of internal energy makes a lot more sense. I mean, it's hugely useful. We can determine how much useful energy is contained in pretty much any chemical compound. This is done by simply measuring temperature changes during chemical reactions. So we know what it is, we know that state functions are great, but really why? Why have we done this? And can I just go look at pictures of cats now? Well, no, because you don't even know why enthalpy is so cool. When a reaction takes place and enthalpy changes, that heat is transferring into or out of actual chemical bonds. Atoms and molecules reacting so that they contain more or less energy, and that energy is either released to or taken from the environment as heat. Those bonds are nothing but energy, and using enthalpy we can measure how much energy they have. And we measure enthalpy with a weird little science called calorimetry. In calorimetry, we have a reaction take place inside an insulated vessel, like a thermos basically, and measure how much the temperature changes, which we can then link directly to heat and thus enthalpy change. Hopefully that sounds like fun, because more about the ins and outs of this are coming in an episode on how to measure enthalpy. Scientists have actually done a lot of the calorimetry footwork for us, so we can actually predict how much heat a chemical reaction will produce. You might not understand what's so great about that, but just imagine, because I live here in Montana, where winters are pretty wintry, I could invent a hand warmer just by doing some calculations on paper without driving to Texas to buy the stuff and do all kinds of expensive experimenting. For that, we have to thank good old Sherman Hess. No, not Hermann Hesse, the gaunt, balding Swiss author and poet. Sherman Hess, the gaunt, balding Swiss author and chemist. Yeah, even the history parts of chemistry are confusing. Hess was a chemist, geologist, professor, author, and doctor, and he also got a law named after him, which is pretty much the highest honor you could get as a chemist. Hess's law, which also kind of led directly to the first law of thermodynamics. Kind of a big deal. Not bad. Hess's law says that the total enthalpy change for a reaction doesn't depend on the pathway it takes, but only on its initial and final states. Sounds pretty familiar, right? As long as you start with the same reactants and end with the same products, the enthalpy change is the same. In order to study this stuff carefully, he looked at the standard enthalpies of formation of the reactants and the products of a reaction. To define standard enthalpy of formation, I'm first going to define what a standard state is. Basically, it's just a set of criteria so that chemists can all be studying stuff under the same conditions. Chemicals in their standard state are at 25 degrees Celsius and 1 atmosphere. Standard enthalpy of formation is the amount of heat lost or gained when 1 mole of a compound is formed.
This shit out. Guy's a fucking pussy. Alright.
Yesterday we looked at, this is called calorimetry, which is you measure the temperature change of a certain solution, normally water. And by measuring out the temperature change, you're working out how much energy has been put in or released from the system. In this question, we had some hexane, which is a gas, hydrocarbon that's being burnt, and it's burning and it's heating. Up our water. We saw our water increase from 20 degrees to 36 degrees, so it's increased in energy, and we can work out the amount of energy with our equation Q equals mc delta T. Our M is 400 grams, our C is our specific heat capacity, 4.18, as it always is for water.
Yes.
And our temperature change is just 36.7 minus 20.
Okay, if 5.22 grams of hexane is burned, the temperature of 400 grams of water increases from 20.5 degrees Celsius to 36.7 degrees Celsius. Dope. Using these results, calculating experimental value of the combustion enthalpy change of C6 C6H14. What the fuck is C6H14? Is that hexane? Yes. Yep, probably is.
8.5, the change in temperature.
And the molar mass of it is 86. Okay. So we can find out, we've got M, we can find out the moles, then we can probably find out the concentration. We can find out the moles and then we'll do some fucking...
And by using that and working out the number of moles of hexane, we can work out this number, which a lot of you did in the Google Classroom post, which is fantastic.
Cool.
There's a second part to this question, which I didn't go into, and that was why I explained why this value you obtained was less than the theoretical value. And this is called the accuracy of this technique.
We talk about... You talk about standing conditions and you talk about like heat escaping from the system maybe.
There's a couple reasons why it's not so accurate, but the main one is heat. This is not a perfect system. Heat is going to escape. Heat can escape by when you burn the hexane, you're not just heating up the water. The energy is going into heating up the tripod, or heating up the glass, or just escaping into the air. These are all ways that heat could escape and not go into heating up the water, which is what we're measuring. Cool. So that was just something about the accuracy of this technique. The next thing we're going to move on to is something called the standard enthalpy of formation. This is given by an F. This F means formation. What this means is 1 mole of a substance formed from its constituent elements. A bit confusing, but we're going to show you an example and it's going to make perfect sense. Here we have propane, C3H8, propane.
Dope.
And we're trying to write out an equation to show the standard enthalpy of formation of propane. When we form propane, what we're going to do is we're going to make it from its base elements. Its base elements in this case is carbon and hydrogen. Carbon is found in nature as a solid, carbon solid, and we have 3 of them. So we have 3 lots of carbon solid. We also have hydrogen in it. Hydrogen is found in nature as H2. You never find hydrogen just by itself, it's always paired up as hydrogen gas. So you have H2 and 4 lots of H2. These are going to combine and they're going to release a certain amount of energy when they combine to make propane. And this is propane gas. And this energy that it releases, we can work it out as the standard enthalpy of formation. So copy down these notes into your books, including the example, and then we can move on. We're going to try these ones in our Google Classroom post.
Oh, yo! Okay. Dude, I've done one. Oh my god. Enthalpy of combustion. Fucks. I do that every day. Combustion definition. Alright, let's have a guess. CH4, that's fucking easy. C, probably a solid, plus 2H2. Which is a gaseous at standard condition, goes to CH4, which is, I believe to be a liquid at room temperature. CH3OH. Oh, dude, CH3OH, that's cool. CH3OH. C plus H3, so 1.5 H2. No. 2H2 again, CH3 plus half of O2 goes to, what are they all? Carbon is solid room temperature, hydrogen is gaseous, oxygen is also gaseous. CH3OH, which is in fact a liquid at room temperature. I'm just making this the states up for CH3OH and CH4.
A few of them like them, but we can try these as a class. So C4, CH4, we have got carbon solid, plus some hydrogen gas,
2H2, baby.
2 lots of hydrogen gas. G for gas is going to make our methane, CH4. Cool, that's the first one. And this is a gas.
Ah, it says the states there, it's gaseous.
The next one
Just like me.
is, it's an alcohol and it's methanol. Again, we have 1 carbon, so just carbon solid.
Dog.
We have 4 hydrogens, so 2H2. And then we have 1 oxygen. How is oxygen found in nature? Or just in the water around us? Oxygen is not found by itself, it's found in oxygen gas. With oxygen gas is O2. We need 1 oxygen here though, so we're going to write half of O2. Half of O2. This is perfectly okay. And this is going to make our methanol. I can't fit methanol in there, but I'll just write this in here or there. So carbon solid plus 2 lots of H2 gas, which is 4 hydrogens total, and then half of an O2 molecule, which is just 1 oxygen atom. This is the standard enthalpy of formation for these molecules. Cool. We can use this data
Look at these stretch
to
marks
figure
on my
out
arms.
enthalpy changes in reactions.
You guys see that?
So if we can get these notes down into our books, this top note and this note here, what this is saying is that the delta H for our reaction can be calculated by summing the delta H of formation for the products minus the delta H of formation for the reactants. Again, looks complicated. We're going to get into some examples and you're going to see that it's actually not so complicated. It starts to get a bit simpler.
Formation enthalpy change is the sum of the formation enthalpy change of products minus the sum of the formation enthalpy change of reactants. Have a think about that, because combustion is the opposite, and I know that I'm not going to remember which one is which. Products minus reactants for formation. Think it through, and then you'll be able to realize why. Because formation is forming and combustion is destroying. So of course formation is going to be products minus reactants, and combustion is going to be reactants minus products.
So, delta H product
Yeah, formation is when 1 mole of a substance is formed.
minus
Combustion is when 1 mole of a substance is burnt.
reactants. It's always the way in chemistry. Products minus reactants. Alright, here we go. We have this equation here, which is ammonia plus some hydrochloric acid making ammonium chloride. And we can work out the enthalpy change for the reaction. This delta RH, this means the enthalpy change for the reaction, using this formation data. Okay, we do products minus reactants. What's our products? Our products is our ammonium chloride, negative 314. Products minus reactants, we add these both up. And here we go. Negative 314 minus our products are minus 46 and minus 52. And that gets us a value. Our value is negative 176 kilojoules per mole. Notice it's negative, so it's exothermic.
Cool.
This is an exothermic reaction. We calculated the enthalpy change based on this information. Cool. This is a slightly different one, but it's
Let's try and do it. That's combustion, dog. So that's products minus reactants. Kill. CO2, negative 394. Plus, minus. Oh, dude, you are being so bad. Negative 394 is equal to, times that bitch by 5 is equal to, minus water times by 6. 286 times by 6 times by 6 is equal to, then we minus the reactants. It's really just adding it on, isn't it? The answer is negative
It's using the exact same
3,391
process.
kilojoules.
The only slight difference here now is thing. It has a these are not the pure fuel. We've got 5. Notice the 5 here.
Kilojoules per mole.
5 times.
No need to plan here. Shut the fuck up! I noticed that shit. Don't think that I didn't notice that. You thought you were gonna get away with me not noticing that, buddy. Okay, I see how it is. I see how it is, buddy. Okay, let's go back. Go back. Oh, let's drag this here. Let's drag this here. Drag that there. This guy's gay, but that's all good in the hood.
I'm going to show how to calculate how much heat is released or absorbed with chemical equations.
Cool.
So here I have a chemical equation that shows what happens when methane, also known as natural gas, burns in the...
The quality so dulcet.
I'm going to show how to calculate how much heat is released or absorbed with chemical equations. So here I have a chemical equation that shows what happens when methane, also known as natural gas, burns in the air.
Yeah.
So methane, CH4, combines with oxygen to make carbon dioxide and water. But as you probably know, if you burn methane, it releases a ton of heat. And that's what this delta H thing is over here.
I knew that.
This number is telling us how much heat we're dealing with. It's 890.4 kilojoules, which is just a unit that we use to measure heat. Now, just in case you weren't sure whether burning natural gas releases heat or absorbs it, we have this negative sign here. The negative is telling us that this is an exothermic reaction, which means that heat is released. So we want to calculate how much heat is released by burning 27.5 grams of methane or natural gas. When I'm doing calculations that use chemical equations like this and use a lot of math, numbers, measurements that are in grams, like 27.5 grams, are not particularly useful. I really want moles. So the first thing that I'm going to do is I'm going to take 27.5 grams.
Gay fuck. Hey, I'm 17. Cut me some slack. There's this thing that I watched where like you can improve your jawline, but like you get your tongue. No, it rests on the bottom of your mouth, but if you put it up to the top of your mouth, like I just look like a fucking idiot. I thought it was working before. It's doing the opposite. It's making me like. Just look like a fucking idiot.
Of CH4. And I'm going to convert that to moles.
N equals M over M. I've got the molar mass. That'd be 16. That'd be 20, wouldn't it?
Here's how I'm going to do it.
No, that'd be 18. C is 14, right? H is 1.
I'm going to use a conversion factor that includes the molecular weight or the molar mass of CH4. I'm not going to talk much about moles.
Oh, it's 12. My bad. So that's 16.
Here, but there are other videos on that topic. So I have grams CH4 up here, and I have grams CH4 down here. They're top and bottom, which means they're going to cancel out. And when I do the math, I'm going to get 1.72 moles of CH4. So So now I know how many moles of CH4 I have. At this point, I can go up.
Dude, my sister does not have a lot of debt from uni as well. She's got $45,000 in debt. That's not a lot of debt, dude. There's a chance that I come out of uni with no debt. There is a chance that I come out of uni with no debt. That'd be crazy, wouldn't it? I mean, dude, I'll have over 20k in a car going into uni. Easy.
And take a look.
No side hustles, and I'll probably come out of uni. By then, one of my side hustles would have blown the fuck up. Whether it's garage selling, probably not. That'll probably be a side thing. But I'll probably have be holding inventory by that stage. I'll probably have a gym brand by that stage. Have built capital through a branded dropshipping store. Then be able to actually start a business. Just imagine that, just going out of uni and starting a business immediately. You've already got the capital. You've already got $100,000. That'd be sick. That'd be sick, cunt. Alright. I'll be back, homie. Stay hard. Might as well just end the podcast here, huh? Shoo. Shoo. How do you even do the tricep flex? Shoo though, look at this, huh? Who's this big guy? Who's this fatty? I can't wait to... It'll be cool to slim down and see what abs I've got. See my ab insert. Right now I've been bulking for 8-9 months. But I reckon I've got some fucking solid abs. I want to work on my lower chest too. I want more of a shelf. When you're standing here and look at me, it doesn't look like a really defined shelf. You can see it side on, my chest looks good. But I don't really look like I've got that shelf, you know. Anyways, that's the podcast. See you.